Okay. All right, so let's talk about the
Pools.
no, not pools, not pools.
Okay.
It doesn't matter. As long as she doesn't do like something weird in class, you know.
Tell us about your loving relationship. I think
She's doing a great job. Remember, 19 days, we should have the implant on the embryo. So and she has to inject herself every day. So well, potentially we'll know, yeah, the day after if it holds, you know. It's all right. So look, imagine we have here a distribution. Obviously, it's look at the shape. We'll say this is the population. I'll say we have access to the population and all the entities within it. And let's say we did the mean for it. So this here we would call the population mean. You added up all the numbers and you divided by a total, you end up with the population mean. And then you went ahead and you just, yes, I'm teaching.
I miss. Oh my God, you're in Zoom? Why are you in Zoom?
Because I'm recording.
You're what?
I'm recording.
Oh, right. Anyways,
It's not wrong.
how are you? Oh my God, your hair grew.
Yes,
You're fit.
I'm fit.
Oh my God. I know. Oh, looks weird.
Looks good, right? So
We'll have this conversation. So
take care. Yes. Okay, so the population mean you find it by adding up all the numbers and dividing by a total. Imagine you had access to a population. There's a billion numbers, and you add them all up and divide it by a billion. Let's say you have, I don't know, you just add up all the numbers and divide by a total. That's how you get the population mean. All right, how do you get the mean? How do you get the mean? You add up all the numbers and let's say you have, we weigh everybody in the class. Yes, that's it. That's the population mean. You can't. I mean, you can. It depends how you define it. But usually the population is too big, right? So usually we can't. But let's assume we do. That would be the population mean. Well, yeah, I would have to give it to you for now. Because what happens is we don't have access to the mean, to the population mean. So what we do is we use an estimate of the mean, which is a sample mean, but we're going to get to that next chapter, which is next 9 weeks. All right, and then let's say you computed the standard deviation. So this here would be called the population standard deviation. Now, let's assume you started taking samples from this population. If the samples are at least 30 in size, if the samples are sufficiently large, saying at least 30, and we're doing a samples, we did sampling distribution of sample means already?
Will you divide the one by the other?
Yes, by the square root of n. Okay, so we did this? Okay, let me just finish this and let me extend it. Fair enough? And we'll do, because everybody left the class, we'll return and do it next class. Yes. Okay, so if sample is bigger or equal to sample size is at least 30. No, we use n. Trust me, we use n. What's the resulting distribution going to look like? What do we say it looked like then? We said it was approximately normal with a mean, which we said the mean of means, right? The mean of means equal to the population mean. and the standard error or the standard deviation of your sampling distribution of sample means is going to equal to the population standard deviation divided by the square root of the sample size. That's essentially a central limit theorem.
I've never done that.
I'm really trying to pay attention. But she keeps
No,
on,
you're not.
she keeps
You're
on writing,
pushing me.
so writing parentheses. I'm like, done that. It's not funny anymore. I'm being funny.
Do you have Wi-Fi with it? You guys have Wi-Fi with it?
The next part of this theorem said that if the original population was already normal, if this was already normal with its mean and its sigma, then any size n for the sampling distribution of sample means would also be normal with the same mean and a sigma x bar, sigma divided by square root of n. But this one here would be normal, while this one here is approximately normal. I will. Okay, so in this case here, we started with a population, a distribution whose shape is not normal. So we were obliged to pick samples to form a sampling distribution of at least size 30. And that would guarantee that the resulting sampling distribution of sample means was approximately normal with a mean equivalent to the population mean and a standard deviation, which was the population standard deviation divided by square root of n. In this case here, the original distribution was defined to be normal. Therefore, the resulting sampling distribution of sample means is also going to now be normal for sure, but with a mean that's equivalent to that population mean and the sigma being sigma divided by square root of n. And that in a nutshell is a central limit theorem. How do we find what? I gotta give it to you. Or you gotta pick it.
All you have to do is divide O by the n squared.
By square root of n. Not n squared, square root. I know what you meant, but
Idiot.
that's mean.
I gave him $1.
You gave him $1, so now you can say anything to him. All right, so let's talk about a problem and where we're going with this, and that I'll pretty much wrap it up there. So here's what happens. Let's say you start with a population of men's height. And the mean height of men is 69 inches. That would be 5'9". That's the average height, give or take 5'9", 5'10". Now, the population standard deviation will be approximately 2 to 3. Let's just say 2, just to keep things easy. So that is the population. Now, we don't know if the distribution is normal or not. It might be. But what we're going to do is we're going to take a samples of size 36. So I'm going to say we're taking a sample of size 36. And I'm going to ask you, what's the probability?
So it's not gonna be normal.
Well, size 36 is more than 30. So the resulting sampling distribution of sample means will be approximately normal. And let me get to that. So here's what I want you to see. What is the probability? What is the probability? The height. I'm gonna write the mean height, sorry. The mean height is greater than 65. So this word here, the mean height, is important because that tells me we're dealing with the sampling distribution and not the original population. So what we do is we say, hey, the resulting distribution is gonna have a mean of 69 with a standard deviation of 2 divided by the square root of 36. Which is, in other words, is 1 divided by 6, which is, what's 1 divided by 6? 2 divided by 6, sorry. 2 divided by 6, which is 1/3, which is 0.333 forever. Now, the probability of mean height is greater than 65. Well, here's greater than 65. And we write X bar 65, and we shade in greater than. What is the probability that the mean height is greater than 65? 65 is to the left of 69. Remember, this is mu's X bar here. So we say Z equals X bar minus mu's of X bar divided by sigma X bar. So that's 65 minus 69 divided by 2 divided by the square root of 36. Notice I've taken great pains to write that out. Because in reality, our new z-score formula looks like this. We just write it like this. This is our new z-score formula. So this is going to be -4 divided by 1/3, which comes out to be -12. Comes out to be -12. So if you look on your table, and you try to figure out -12 and this area here, like -12 is not even on your table for z-scores. So that means that the area to the left here is like 0.00000001. It's like, it's some ridiculous small number. It's almost 0. So therefore, this is like 0.9999. It's really big. So the probability that the mean heights for a sampling distribution sample mean is greater than 65 is for all purposes 1. So if you want to, you could just write the mean height, 65, is 0.9999. Practically 1. Yes.
Mr. How do you divide -4
Well, you could do a few ways. So the question is right here, -4 divided by 1/3 is really equal to -4 times the reciprocal of 3, if you remember from algebra. So that comes out to -12. Or in your calculator, you can go ahead and just go -4 divided by parentheses 1 divided by 3 and press equals, right? And it's gonna happen.
Can you just do 1 divided by 3 and then what
You-
you get?
Well, so if you do 1 divided by 3, you're gonna get 0.333333333. So then you take -4 divided by 0.33333. Sometimes the calculator is not gonna give you -12. It'll give you like -11.99999, but it's really -12.
So every answer we just put point.
No, in this case it is that. But this is the probability for a sampling distribution of sample means. But now if you would have redone this problem, I would have said, what's the probability the height is greater than 65? If you would have done that. So here you have it. Here's 69. The mean is 69 still. Sigma is just 2. Here's 65. I want this area. But when I do my z-score now, I have 65 minus 69 divided by 2. That's z equals -4 divided by 2, which is -2. Therefore, this situation here is modeled by this here. See, these are x's, these are z's. And now we look up the area for -2, right? I think it's 0.1587. So to figure this area out here, it's 1 minus 0.1587. So that's 0.8413. Let me make sure, because I'm doing this by memory, and right now I need to eat something. But I'll eat when I get home, of course. Look, Katie,
Oh, you did that away? Oh. I mean, it's covered in.
the spit.
There's a gum on the back.
Yes,
So I think it was doing this stuff.
but how do you know I threw your work? Look, you did good work. It was fine. You did it all right. All right, let me take a look at the answer here. It's
Yeah.
-2.0 is point. Oh, no, I messed up. It's 0.0228. 0.0228. So let me go ahead and erase that. Thinking of something else. 0.0228. And so how do you find this area here? It's 1 minus 0.0228. Now notice the difference. 1 minus 0.0228 is, I messed it up. 1 minus 0.0228. That's a 0.9772. So in this case, this comes out to be the probability of the heights being greater than 65 came out to be 0.9772. But the probability of the mean heights being greater than, the mean heights being greater than 65 was practically 1, was 0.9999. So that's the difference between a sampling distribution and the original population. Does that make sense? Okay, so let me go ahead and stop the share. No, let me not stop the share. Look, we don't want to see the class though.
Are we done?
Yeah, we're done.